Okay, so now we know how particles sit on liquid-liquid interfaces, and if you make stuff really small, that there might be a deviation. Good news is small stuff still sticks pretty well. So what can we do with this? So one thing, what we developed at Warwick a few years back, well, the first paper was in 2005, so it's quite a while back, but we developed it, is that you can, if particles stick at liquid-liquid interfaces, you can almost say, well, the molecular equivalent would be a surfactant molecule adheres to a liquid-liquid interface, so maybe particles can act the same as surfactant molecules. And so you could imagine if I have a mixture of oil and water, and I have particles present there, and I shake, that these particles go around the droplet, and maybe I can influence the size of the droplets if I vary the amount of these particles. So these particles, they can decide to sit in a water phase, they can decide to sit in the oil phase, or they can decide to sit at the interface. Now, in order to stabilize an oil droplet in water, the particle has to be, you know, relatively hydrophilic, and it basically likes to sit more into the water phase. So you could argue, well, okay, if the particle is relatively hydrophilic, it's either in the water phase or on the interface, but it will never be on the oil phase. And that's a relatively good assumption to make. So if we have that, you can say, okay, we've seen that these particles stick pretty heavily. So once they bump into the droplet, they don't really come off anymore. Whereas surfactant molecules quite easily absorb and desorb. So you might argue that it might be rather difficult to see this happening. So if you would just shake, maybe the adhesion energy of the particle is too large, and therefore you can't really match droplet size with respect to number of particles. So in order to overcome that, in this case, we're actually a bit lucky, because what we wanted to do was make really, really small droplets. And for really small droplets, you need high shear. And we've learned already in miniemulsion polymerization that we do that, for example, with ultrasound. And ultrasound is a lot of kT, a lot of energy, which means now the process, whilst the ultrasound probe is on, particles can adhere and come off, on and off the interface. Exactly the same thing as molecules can. And with a miniemulsion polymerization, we've seen that, you know, if you add more molecular surfactants, you get smaller droplets. So in this particular case, the argument would be, if we add more particles, and if the partitioning coefficient, so that is the amount of particles in the water with respect to the interface, stays roughly the same, we should be able to control the drop size. And if we can control the drop size, that's really quite interesting, because we can make particles or armored droplets of a variety of sizes. So we can have control over that, which would be good, potentially for, you know, applications. So what on top of that can you do? Well, you can easily see if the droplet is, well, in this case, a monomer, then you could polymerize the droplet, so you'll end up with a polymeric sphere that is armored with clay platelets. So, and then, you know, you might wonder what you use this for. So let's have a closer look at this. So here you see an AFM picture of a film that has been made from these type of materials, and you'll see that the top, well, the surface looks a bit bumpy, yeah. And the previous picture, I've shown you that these clay discs were Laponite clay discs. They're a, well, disc size 25 nanometer by 1. So now the question is, are they really discs, and what did they look like? So what we did, there's one large particle here. So we zoomed in on top of the surface of the large one and just checked whether we could see any discs lying on the surface. So what you see is there is stuff that lies on the surface. So here you see a zoomed in AFM picture. So the square is 250 by 250 nanometer. And you see that there is some bumpy stuff on it. And the best image you actually get from the amplitude image, the middle image. But you don't really see, they're not really ideal cylinders, right? They're a bit like broken roof tiles, a little bit. But, you know, relatively close. About 20, 25 nanometer, you get 10 of these things roughly on one length scale, so it kind of works pretty well. So the question we need to answer now is like, how many of these disks do I need to cover a droplet? So you're going back to geometry, and can you work out, or can you predict what this behavior should be? So this is the problem, right? The problem is how many disks, and we know, well, let's just go back to our ideal disk, 25 nanometer in diameter, one nanometer high. How many disks can I put on a sphere of a certain size? And this question was already raised in the 1930s by Tammes. And then you can kind of go like, well, this can't be very difficult. But unfortunately, it's not a trivial problem to solve. So, and this problem is actually quite related to, well, a related problem. The Thomson problem is like, how many charges can you put on a sphere? And there they put them as far away as possible from each other. So how many spheres, on how many disks on a sphere can you place on top of each other? And it's not easy. So, so for this work, we made our problem a little bit more simple. So what we did is like, okay, let's just put all the disks next to each other in a square packing. With square packing, I mean that, you know, you have a neighbors, that, yeah, well, they all nicely lined up together like this. Hexagonal, obviously they'll have 6 neighbors touching them, surrounding them. Now you have 4 that touch each other. And we're going to assume that all these disks have exactly the same diameter, the same height, and we're going to just completely ignore that these things are on a curved surface. Yeah? So the only thing that we need to know, if we have oil droplets, is the total surface area of all the oil droplets together and the surface area that my clay particles could cover if I would arrange them like this. Yeah? So my total number of clay particles I get from how much clay I add to my system. So I need to know the density of the clay, which is 2.57. And then obviously I need the density of oil. I need the dimensions of my clay, which was 25 by 1 roughly. And I need to know how much oil I have. And then you can work out this coverage number. And the coverage number is basically the amount, the total area my clay can occupy, divided by my total area of oil droplets. So it's a nice exercise. So people were asking, what is a nice exercise to as a workshop type of problem? Well, that is a nice problem to figure out. So you kind of want to figure out whether you can come up with that yourself, with that equation. So the only thing that you combine here is just surface areas and densities. So okay. So this is the same thing, but now applied to the system what we were talking about. So you can come up always, if you do chemistry, you can make a mass balance, and you can basically say, okay, the amount of clay that I put in my system, C0, and I go in grams per gram, right? Grams of clay per grams of water, because that's easier to measure. So forget about mole, because I've got objects here, it's a bit difficult. So just gram per gram. So it's a dimensionless concentration almost. So that is the amount that's on the surface, the amount of clay platelets on the surface, with the amount of clay that's in excess. And in excess, I mean, in this case, in the water phase. So I can basically revert that a little bit. I could say, okay, the amount of clay that's in the water phase is the amount I put in minus the stuff that gets absorbed. And with the rearrangement of the equation on the previous slide, you can calculate how much is absorbed if you assume it's full packing. So what you're left with is basically this expression that links it to the concentration of oil droplets. And because we had this reversible partitioning, you could even argue that the second term, so the concentration and the diameter of the oil droplets, so the diameter of the oil droplet, would scale with the amount of clay that I put in. So you could argue that the amount excess in the water phase would be what I put in minus a function of what I put in. And that should match quite nicely. So let's have a look. We've done a lot of experiments. So what we did is like lots of different amounts of clay, keep the oil to water ratio the same, zap it, polymerize it, measure particle size distribution to see if we get a logical expression. So if you do that, so if you plot the amount of clay that you put in, and you basically calculate CXS with the equation that was given on the previous slide, what you'll see is that a lot of these experiments, they fall quite nicely on the two dotted lines. So the two dotted lines are two series of experiments on which one case where we added 4 weight % of hexadecane to the droplets of styrene, and the other case 8 weight % of hexadecane. Just to recap, why do we have to add hexadecane to an oil droplet if the oil droplet is really small? What's the function of this? Yeah, to stop oscillate ripening, or basically retard oscillate ripening, so the droplets remain stable for a long period. So, and the dots that deviate from this, so you see 2 black triangles here, and they're not on this line. So you could say, well, Stefan, you're talking nonsense, because not everything lies on this line. But if you would put in the particle numbers there, then the droplet size, we use so much clay that the droplet size should be so small that we have a geometry conflict. So the droplet should then become about, say, 100 or 50 nanometer, whereas my clay is already 25. So it doesn't really fit nicely on it, and we get some geometry issues, and then you start to deviate. The good news about this approach is that before we do the experiment, we roughly know how big the particle size is going to be. That's very useful. So, because if you say, I want to make these particles and I want them to be 500 nanometer, you just plot it on this line and say, okay, you need to use so much clay. And then we know exactly how big the size is going to be. So it's very useful. So here you see, if you would have these droplets, and if you would polymerize this system, this is typical, conversion time data. And so the largest particles go at the slowest rate, and the smallest one go at the highest rate. Why is that? Why do small particles, why is the overall rate of monomer consumption and thus of polymerization, why is it higher for small particles than large particles? Yeah, what does that relate to though? So if you go back to emulsion polymerization, we talked about different models, right? We talked about 0-1 versus pseudo bulk, yeah? Yeah, independent polymerization. So yeah, so each particle can be considered as a reactor. So what is the difference if I make my particle small? Yeah? Exactly. So that effect is called, radicals don't terminate. So that effect is called compartmentalization. So the particles become smaller, compartmentalization kicks in, and the rate of polymerization becomes larger. So now there's a trick what you can do in order to, because it's kind of difficult to see on this plot, so you can do a clever trick, right? If you do this experiment, you basically can get that data what you've got. So it's basically, is compartmentalization important? So you have monomer consumption over Kp, and it tells you something about the number of radicals, yeah? And you can do the equivalent bulk polymerization. And the interesting thing in a mini-emulsion is that in this case we use AIBN as initiator, so you could argue, well, I'm just going to do a test reaction, styrene AIBN, I'm going to follow conversion over time, and I'm going to divide these two upon each other. So I divide the data that I had on the previous slide with the equivalent bulk polymerization, and if compartmentalization is important, then that ratio becomes larger than 1, and if it's not important, it stays flat, and it's 1, right? So let's see whether that makes sense. And it does, right? So here, it's a bit chaotic, but on the right-hand side, next to these indexes, you'll see the diameter of the particles, and here is the ratio of the two rates of reaction as a function of monomer conversion. And you see for the larger particles that are like 600 nanometers, you see roughly that it's 1. And then for the smaller particles, you see that there's a massive increase in rate of reaction. Now there's a few distinct regions. So you see these plateau numbers here, these leveling out bits here. And that's an indication of where you want to be. So you know, the smallest particle polymerizes 7 times as fast as you would expect based on bulk kinetics. But you also see there's a massive retardation effect before you reach that. And we argue that maybe the clay on the interface potentially traps some radicals, and that's why it doesn't react. But that's speculative. And the bit why it goes up here, why it deviates, well, we followed the rate, as you could see on the previous slide, the rate of bulk polymerization was followed as a straight line. So we don't take the Tromsdorf effect in, and obviously into account, and obviously that starts to become important there. So that's the kind of trick what you can play with experimental data. So what can you do with this stuff, right? So you've made these particles, and what can you do with it? So this is quite interesting. So the advantage of a miniemulsion polymerization is that you can polymerize monomers that have a very low water solubility. So for example, lauryl acrylate has a very low water solubility. And in emulsion polymerization, that's difficult because you have to rely on monomer transport. So what did we do? So we basically made these armored particles, lauryl acrylate, polylauryl acrylate, which is like a bit like chewing gum, right? It's really soft. It has the side chains can crystallize a little bit potentially at 0 degrees, but the TG is very low. Yeah, so it's quite a gooey thing, armored with clay particles. And then one of the applications could be stickers, pressure-sensitive adhesives, which are, it's a sticky material. And how does a sticker work? Well, basically, it's a gooey mess, right? So a good sticker material would be, a waterborne sticker material would be for labels as a polybutyl acrylate latex. So a polybutyl acrylate latex has a TG of minus 54 degrees Celsius. Yeah. So you dry these particles out, they stack on top of each other, and it just becomes a really sticky polymer film. And how do you measure the adhesion force of a sticker? Well, they do that with a machine that has a large metal sphere. So you cast the film of the sticker, the metal sphere comes into the sticker, and then you measure the pull-off force. Yeah, so you just lift that big sphere up, and you check when there's no interaction anymore. So let's do that experiment. So you get a stress versus strain type of experiment. So the black dots here in the black line in the left figure is a polybutyl acrylate sticker material. So you look it up, and you see initially you get a lift off, so you pick off, and then it comes down, and you see a plateau forming here, and that's where you get fibers. Yeah, so you remove this adhesive, you get these fibers, and when the fiber breaks, you have no interaction anymore, it drops to 0. Yeah? So let's put this polybutyl acrylate latex, and we add 2.45 weight% of naked polylauryl acrylate particles. Now, if you think about this, you have a soft series of particles, and you add more soft particles. So there shouldn't be a difference. Yeah? And there isn't. So the green line behaves exactly the same, or roughly the same, as the black line. So no difference whatsoever. So now let's pick this polybutyl acrylate latex and add a tiny bit of Laponite clay by itself. And clay discs, imagine they interpenetrate a bit through these spaghetti chains of polymer chains, so maybe they reinforce it a little bit. And that's exactly what it does. So lift off is the same, and then you see here on the purple line, or the that plateau level lies slightly higher. So your fibers are a little bit stiffer, but they break roughly at the same point. Then you make a blend of these two things. So I've got a polybutyl acrylate latex, my clay particles, and my soft latex dispersed through each other. And then I do my experiment, and what you'll see is exactly the same experiment as the reinforcement with the clay, but no big difference. Yeah. Then you use your hybrid particles. So now you have your armored latex. Do the same experiment at 2.7 weight% of this. This is a fraction, right? Massive difference. So the area under this curve is a measure for the adhesion energy. So by adding 2.7 weight% of this particular material, you can increase the overall bulk adhesion energy of the sticker with up to 70%. So your sticker sticks 70% better by adding a little bit of this pre-assembled structure, which is a massive difference. And I think it's one of the first examples that you can influence a bulk property of a material by adding this particular compound. So what do we think what happens? What we think, but we don't know, is that when you stretch this fiber, you will start to distort this armored particle, and the clay platelets pop off the particle, which dissipates energy, which allows it to stretch further before it breaks. But we haven't got exact experimental proof, so that's something that still needs to be done. So this is a nice application for these type of structures. Okay, so obviously it's a nice story. You can do this with a range of different materials, right? So here we've done, I think we've seen this slide before in the introduction. Here you have silica particles around tiny little droplets. And in this case, we solidified the droplets in order to be able to do conventional SEM and TEM. So on the left, you see conventional SEM unsputtered and on a silicon wafer, and on the right, you see a transmission electron microscopy image. And what you see is that you have these armored raspberry type of structures. Now, if you like geometry, you can go back to this Tammes problem and you can say, okay, I'm interested in how many of these little spheres lie on this big sphere. Yeah? But now the case is a little bit more complex, because it's very difficult in synthetic colloid science to get small spheres monodisperse. Why is that? Why is it difficult to get monodisperse small spheres? Anybody a view on this? So you have particle nucleation versus particle growth. Yeah, they're relatively related to each other. So if anybody got a view on it now? So you get monodispersed spheres if the particle nucleation period is short relative to the total period. Yeah? So, but if you want to make small spheres, your growth period is really short, otherwise they're big. Yeah? So it's difficult to have a relatively small nucleation period, which means there's a dispersity over your particle size, which is generically, 10, 15% or higher if particles become really small. So that's a big problem. So these particles were Ludox silica spheres of 25 nanometer, and they had a polydispersity index of about 14%, which means that we have to take that into account, that there's a size distribution over these small ones with respect to what we've got. So again, modeling comes in, and it's quite a fun story. So let me share a story with you. So the story is the number 12 a magic number in assembly, yes or no? So there you go. So here's a picture on the left of a football, an old football. But nowadays they don't make them like this anymore. They have all kinds of weird stitches. And what you'll find on the football that you have 12 hexagons, which are your white boxes, and you've got 20 hexagons and 12 pentagons. So 12 is on a football. Now, if you shrink a football and you end up with a buckyball, so that's a picture of, who's the guy in the picture? Who won the Nobel Prize for buckyballs? Anybody? Harry Kroto. He's English as well, guys. Come on. So it's like, anyway, Harry Kroto with a buckyball. C60 is just basically a shrunken football. Again, 12 hexagons, or 12 pentagons, 20 hexagons, nicely teamed up with each other. So you could say 12 is kind of interesting number. Here, different pictures. So we have a lipid of a bacteria, and sometimes bacteria have on the outside globular proteins, which effectively are ping pong balls, yeah, if you make it easier, and they assemble on the surface. And so you can see an image here, and you can see, okay, sometimes they're arranged in a square packing, but sometimes arranged in a hexagonal packing, but that would be 4 versus 6, so that's not 12. Then I'm looking at fly eye here on the right, and if I zoom in on one of these spheres here at the top, because they're slightly bigger and easier to see, and I count around it, 1, 2, 3, 4, 5, 6 neighbors. That is not 12. Yeah? I look at sneeze weed, the picture here, do exactly the same thing. You count, and most of them will have 6 neighbors. So you might say, okay, if I'm in 2D, then 12 is gone. Maybe. Yeah? Maybe not. Let's go in 3D. Back to 3D. So we've seen, well, I haven't really talked about it. So if you make monodispersed particles, everybody knows that atoms can crystallize, but particles can do this too. It's just a scaling factor. So if basically things are the same size, they can order, they can pack quite nicely, and they can form crystals. So here, actually, this is, well, this don't work, actually, this picture. It's pretty cool. This is an FCC colloidal crystal of spheres. They're about, say, 150 nanometer in diameter. And what you'll see is that, you know, they're beautifully ordered. So, and in 2D at the top, if you count, you'll have 6 neighbors. And in 3D, how many neighbors do you have in 3D? 12. Yeah? 6 in plane, 3 on top, 3 at the bottom. There are 2 different packing arrangements for this. Which 2? Both cases have 12. Yeah, HCP, hexagonally close packed, and FCC, face-centered cubic. So here the top one is F-centered cubic. So you have layer A, layer B as offset, and layer C before you go back to layer A. So ABC, ABC. Yeah. The bottom bit you have HCP. So you have layer A, layer B, back to layer A. Both cases will have the same coordination number. Both cases have the same volumetric packing density. What's the packing density of an FCC or HCP crystal? Volume per volume, how many ping pong balls? 74%, right? You've hopefully have learned that in some crystallization stuff. But you can work it out, right? You can work it out for yourself. So again, a geometry problem. Now, to convince you that this is really true, so here in this picture, you see, if you look at the central one, you see 6 neighbors around it, and you see 3 little holes from the layer below. That's where the spots where the spheres touch each other there. So these kind of things, these type of arrangements, they sometimes get backfilled. So as in you fill up the holes with titanium dioxide, for example, and you use this as a base for solar cells. So, but again, in this particular story, we were talking about number 12. So in 3D, number 12 is there. In 2D, we have a little bit of debate at the moment, whether it's there or whether it's not there, because we can see 6, but maybe we can't see 12. Okay. So, so this is the story with you know, with the spheres. So related problem again, which is the Thomson problem. How many little spheres can I put in on a big sphere? So we've seen central sphere the same size. It's 12. What happens if I blow up my sphere? Effectively, that's the thing what you want to do. So so in 3D, if the little spheres and the big spheres are the same size, we know the number is 12. What is the number in 2D? What's the number in 1D? So in 2D we saw 6. What's the number in 1D? 1D is spheres on a line. 2. Yeah, 1 to the left, 1 to the right. So it's 2, 6, 12. In 4D, I have to ask your mathematics friend. So you can do 40, 5D, 6D, but I don't know the answer. So okay, let's blow the middle sphere up. The most expensive experiment ever, and you can't redo it anymore. It's a bit of a shame. You rent a space shuttle here, and you go up in the sky, and you do in space, and you do an emulsion polymerization in space, and you can make really large particles because there's no gravity, and you take a picture. This is done in 1985 by Mohammed Al-Azhar. So it's great. He takes the picture, puts it in his drawer, doesn't use the picture. He just thought it was a pretty picture. And you can see like lots of these things have 6 coordinate numbers, but sometimes you see cracks. Yeah. Now the fun bit is in 2002, Waits and Dinsmore had also a similar picture and called this picture a colloidosome, and then it was a science paper. And Mohammed Al-Azhar rented the space shuttle and just kept it in his drawer because he thought it was just a pretty picture. So there you go. So so around that area, so later on, people thought, well, maybe there's something with this packing, right? So Bausch and co-workers in '07 in Nature Materials had a droplet, put monodispersed particles around it, and started to count whether they had 6 or 7 neighbors. Yeah? And what they did is basically, if it was 5 or 7, they had a colored dot. So if it was 5, it's a red dot, and if it's 7, it was a yellow dot. And they plotted that in 3D. And what they found was that in the ideal scenario, if the system relaxed to its lowest energy conformation, you had 12 grain boundary scars. So 12 scars. So even in 2D, when you pack particles around the sphere, there are 12 spots where you'll get a so-called grain boundary scar. 12 places where it goes wrong. So that's fun. So what about our system, right? Because now our spheres are polydispersed. What happens then? Well, how do you model this, right? You can either go, okay, I'm going to use continuous model. There's a nice package out for the people that want to use this. It's freeware. It's called Surface Evolver, so you can download it, and you can predict all kinds of shapes of interfaces if you like. But it doesn't really take into account this polydispersity, and it's really difficult to introduce. So what we did was rely back on Monte Carlo simulations. So you work with Alessandro Troisi and with Sara Fortuna, and what they do is just, they take a large box, put the real particle, the polydispersity in the box, and assemble these things on a sphere. And what people in my team did was just count lots and lots and lots of these particles and color code them, 4 neighbors, 5 neighbors, 6 neighbors, 7 neighbors, 8 neighbors, and then match them up. And then what you can do is that if you do the simulation, you have to have a particle-particle interaction there, and you use a Lennard-Jones type of potential, so like a 612 or a 1224 attractive or repulsion potential. And what you'll see is that the simulations predict, so the simulations are the greens and the red lines, and the experiment is the gray line. If you use a pretty stiff hard potential, so hard sphere interaction, you can see that you can predict how these things rearrange themselves quite nicely on this sphere. Now, that's really important if you want to use this semi-permeable sphere as a porous structure that you can diffuse things in and out. So why do you want to know what effectively the space in between 3 of these spheres is when they touch each other? So do people know if I have 3 spheres, how big is the gap in between? The Sartre, 1640 something. Anybody an idea? So if you do it for monodispersed spheres, the gap in between is roughly 0.15 times the radius of the sphere. So if you want stuff to go in and out in a perfectly flat layer, you know what the space is and how big stuff has to be in order to diffuse through that layer. However, on a curved surface, because of these grain boundary scars, sometimes you have bigger gaps. Yeah, so it's like having a permeable object, and if there's a big hole in it, obviously everything goes in and out there and not through the rest. So it's really important for controlled release to understand this. So here you see what happens, right? So in the ideal case, in the monodispersed case, you'll have beautiful, 5 and 7 sometimes. Most of them are 6, which are the green ones. And then if you make it more chaotic, so if you increase polydispersity, you'll get some your fractions of 5 and 7 and 4 and 8 go up, and the number of 6 gradually goes down, and you fade out here. So it starts to become a mess, right? And you can plot this radially, like you plot the world, basically. If you unzip the world, you get the same picture here. And in the monodispersed case, you beautifully see you'll have, if you count them, 12 regions, 12 grain boundary scars. And then you look at the most polydispersed case, so the picture on the top right looks like confetti, right? Like a mess. And you go like, my number 12 is gone. Now here's the trick. The number 12 is not gone. Because if you call 5, say 5 is -1, 4 is -2, 7 is +1, and 8 is +2, if you add all those things up, you'll end up with number 12. So it's still there. So number 12, I think, truly is It's a rather magic number. Okay, that's where I want to stop for now.